So welcome everyone. Thank you. Congratulations for making it to the last day. So yesterday I stopped at we're discussing optimization of a training of machine learning models, training of ML models. And the question, I motivated the fact that we will be working with a stochastic gradient dynamics. Gradient because somehow we don't want to go second order. And stochastic gradient because we for computational reasons. So maybe I'll start by considering this. How do I call my loss function? So so the typical loss function, just to set a back notation, would be some empirical risk plus possibly some regularization term. And maybe for simplicity, I'm just denoting it by f of theta here. And to be clear, just to recall the notation, it would be something like Ly f theta xi sum from I equal 1 to n and then plus theta. So let's, gradient dynamics would be the following. So standard gradient dynamics, I would say. So it would be a dynamics where we would start from a theta 0 given. So for neural networks, typically random initialization, the way we discussed yesterday with some scaling of the variance. And then we iterate upon the parameter by saying that we take the new parameter to be the previous one minus gradient of f of theta n. So that this would be, and so here this parameter, in machine learning, it's called the learning rate. In physics, you would call it a time step, and this would be a discretization of the gradient dynamics, discretization of the gradient dynamics, which would be theta dot of t is equal to minus gradient f of theta of t. So, is everyone familiar with gradient dynamics? That the idea here is that you're converging to the closest local minimum. So if you start from here, you go there. If you start from here, you go there. If you start from here, you go there, etc. The way you can see, is that this dynamic stops when gradient of f vanishes. So unless you start from some critical point, you're converging to the closest local minimum. So gradient dynamics has its advantages. The point here is that gradient f has a cost O of n. When you look at computing the gradient here, a gradient f of theta is lambda, the gradient of omega of theta, with possibly here a notion of gradient to be made precise when you have a constraint that's non-differentiable. So it's technically from, mathematical, comment is that if you have like a lasso penalization, you have a non-differentiability at 0, and so you need to generalize the notion of gradient to subgradients. But let's not care about that. Here, the main point I want to make is that so let's imagine, is that here this is, you have to sum n terms to get the derivative. So here by dzl, so I'm imagining L to be a function of y and z. So I'm taking the partial derivative with respect to the second argument. Up, f theta of xi, and then I'm multiplying with by the gradient of theta with respect to xi. And so that part typically is what we discussed yesterday. For neural networks, this would be computed using automatic differentiation. But you see that, this formula clearly says that gradient f has a cost of order n. So this is expansive, and it's possibly overkill or useless, at least at the beginning, at early stages of optimization. Somehow one can imagine that at the beginning you've done some random initialization, so you're really starting from something that's not particularly relevant. And so even some approximate gradient is sufficient. Maybe you don't need an extremely accurate gradient because you're anyway so far off the local minimum. And so here we'll be looking for some approximate gradient, which is something which is random and unbiased. And so that's what I'm discussing here. So I will be denoting it by g hat t of theta. So that's the maybe I should have put t's here. It's more customary in machine learning, maybe to put t's. So I would say that there are three. So you want the unbiasedness property will be that the expectation of the average of my stochastic gradient respect to theta for say at value t minus 1 given theta. So we will have some randomness which is somehow conditional on the state you're at. It will not depend on the state. Essentially, it will consist in taking some data at random in a way that does not depend on the state. So we will want that if you fix the current value of theta, the stochastic estimator you have of the gradient is unbiased. So we will want this equality to hold. And there are, I would say, three strategies. In the end, it's essentially two, but let's pretend there are three. So three strategies. The first one, it corresponds to something that's called stochastic approximation, and which dates back to Robbins and Monroe, and that's the 50s. Robbins, Monroe, is there E? Nope, there is not. So the 50s. And it consists in taking g hat t of theta, which is lambda, so the regularization part, plus gradient respect to, plus this partial derivative, so dzl y capital I t. So here, this is the important thing is that I will take 1 point at random. So it is a uniform random variable on the set 1 to n, which is independent of theta t minus 1. So at each step, you will choose at random one of the n data points. And I'm denoting its index by yt. And so your approximator of the gradient will consist in replacing the empirical average over all data points by just the value for that particular point that you selected. So somehow my order n sum here has been replaced by just one element. So that's why it's cheap, because you only have one element left instead of little n. So that property is satisfied. And now you can check that indeed the average of, let's say, any function h of it, so the unbiasedness comes from the fact that the average of any function of it is exactly 1 over n, the sum of the values of h for this value I. It's because this it here is uniform over 1 over n. I see a strong silence, a dense silence in the room, which leaves me to think that many of you are a bit wondering about that equality. Is it clear for everyone, or? So I mean, if you have troubles with that, let's imagine the situation. You're at step T. You choose one index at random. You have 1 point. You choose reproduce. Enfin, you choose another one. You have another point. You do it a third time, and you do it a billion of times. And in the end, you count how many ones did I have, how many twos, how many, etc. until n. And so the fact that you do it over and over again, I mean, in average, you will choose each point with more or less with the same frequency, up to statistical fluctuations. But so in average, what you will have will be an average of all those values that you get. I mean, h here is any function. I was just a bit lazy to, I mean, that's my h of it here. Just out of laziness, but I mean, that's really what I mean.
So if you take only 1 point, it's a very bad approximation.
It is.
But the fact that you do a lot of iterations, then you make.
You're going to average out the noise to some extent. I mean, I'll rediscuss it a bit more precisely, but I mean, that's really a stochastic approximation from the 50s. And in practice, indeed, no one does that with just 1 point, but somehow that's the motivation behind. And what people actually do in practice is something called mini batching. So I guess maybe you've all heard the term. And mini batching comes in 2 flavors. One which is more frequent than the other. And in fact, in practice, people don't exactly do mini batching, but they do something which is a more deterministic version of it based on shuffling. So we'll go step by step. So let's think about mini batching. And here there are 2 options, with or without replacement. And so usually people would do without. By that, I mean that I'm going to, now I will have a IT, which is supposed to be a curly IT. I don't know, the previous one was a straight one, just one number. Here it's supposed to be a set. So that's a subset of 1n of cardinality m. Cardinality m. And I'll try to make my m's with like 3 feet and the n's with 2 so that you can distinguish them. If there is some confusion, don't I trust that you will ask. So you select m points among the n's. So you can do that with replacement. So you take 1 point from 1 to n, then another one, and so on and so forth. And maybe you have repeated indices. Maybe you don't, but maybe you have. And if you do it without replacement, you're directly taking m points out of the 1n, and they're all different. So I mean, depends a bit on what you would prefer to do. If m is smaller than, so if m is much smaller than n, there is only there is no actual, no, there is only a mild difference, but so there is no actual difference. But of course, if you consider little m is equal to little n, we're in the bootstrapping case we discussed yesterday, and then you've got lots of repeated indices and lots of indices that don't appear. But usually the cardinality of m is rather small, and it would be something, say, in practice, 68 to 256 out of n, which would be of order of, I don't know, 1,000 to millions and more. So it's something that's substantially small. In practice, people take powers of 2 for m because it's on GPUs. If you work on CPUs, you can live with a decimal of powers of 10. But for GPUs, makes a difference whether the batches you're considering are powers of 2, because that makes computations more efficient. And so that's why, I mean, those are magic numbers you see in ML papers. So we take those points, and then we consider g hat of theta, which is still our regularization part. and then something which is 1 over m, and then we're summing indices in our random set. So we're taking the average over the random set. And so those h of I with the notation of h I've introduced over there. So stochastic approximation is this thing with m equal 1, just taking 1 point and having that estimator. So that's the generalization to having more than 1 point. And somehow it's I would say it's reasonable that this works when you do with replacement. I mean, all those indices in the IET sets are independent, and so in effect, from this unbiasedness property here, you directly get the unbiasedness property there. And if, in fact, you can have a similar reasoning when you do with replacement. Essentially, here you have a stochastic estimator of the average over the data set. Is that fine, mini batching for everyone? So we're
when they give that replacement, they do a lot of mini batches, and when they have done the whole.
No, we come to that. I mean, that's shuffling, the notion of epoch, and so on. We're not there yet. So maybe a few properties here is that the I mean the covariance of the noise. So here the covariance of G. No, maybe let's write it even more intuitively. If you want to make the statistical analysis of this, I mean, it's convenient to say that this G hat of theta is the exact gradient you want, G hat of theta, plus some noise, ZT. So some vector noise. That's a right way to see it with. So this noise is centered. I mean, it's mean 0. That's because you have an unbiased estimator. But somehow more importantly, the covariance of the noise, which is a matrix, is something which scales as 1 over m at the first order somehow. Meaning that with or without replacement, when m is small compared to n, you have something that here is of order 1 over m. Which makes sense somehow, because here you have an average over m terms, so you're expecting somehow that the variance is of order 1 over m. Is that statement clear to everyone? So that's in effect, I mean, to answer your question, a way of reducing the noise by just taking more terms in the stochastic approximation. But in the end, what we have, and that's is that we don't exactly, we should think of a stochastic gradient dynamics as being something, as a dynamics which is of that form. So stochastic gradient dynamics. Yeah, it will. No, I mean, it will. If you do with replacement, it won't, because you still. But yeah, if you do without replacement, the covariance should be 0 for m equal n, and that's why there is only an approximate equality here. I mean, lecture note, there is a painful exercise with a 1-page correction to show that the covariance would scale as a 1 over m multiplied by 1 minus m over n, something that vanishes when indeed m is large. Let's say we mostly care about the small m regime, small in front of m. But yeah, fair point. So I mean, in practice, what you implement when you do a stochastic gradient dynamics is this dynamic. So you replace the exact grad f by its stochastic approximation. And the way you should think about it is by rewriting the dynamics as exact gradient dynamics plus some noise. And here, the point, and that's a bit, I don't know, how many of you are familiar with stochastic differential equations? Well, some of you. for those who are not particularly familiar with that, maybe it's time to think about something else. So let's think about the notion of a continuous between quote limit. One point for those of you doing SDs is that here, in fact, we have the noise is multiplied by a factor eta and not square root of eta. So if you were discretizing a Brownian motion, typically the noise would come, you would have a Gaussian with a factor square root of eta in front of it. Here, this term here, because it's an average over a certain number of terms, when little m is not so small, so if I'm in a regime where m is much larger than 1, but still much smaller than n, I can think of that noise term to be approximately Gaussian with some covariance. And so I end up with a Gaussian multiplied by a factor eta. So I have something like theta t plus 1 equals to theta t minus eta grad f of theta t plus eta some covariance matrix, which I'm going to write comment m, something like that, and then some Gaussian random number, more or less, and maybe this scales as little m. So maybe some C matrix divided by m. So I essentially have something like that, and this should be thought of as a discretization of a stochastic dynamics, which would be that one with some noise which is of the order of square root of eta. So here C, sorry, square root of m because the variance is of order m, and then dwt. So it's really some form of overdamped Langevin dynamics with a very small temperature. I mean that it could be understood that way. And so that's so I do realize that maybe this remark is a bit too advanced for most of you because stochastic Langevin for small temperature. There was some lecture on SDs a few years back by Tony Leliev. So I guess those of you who were there a few years back, Tony, for sure talked a lot about that. If you're not familiar with SDs, I mean, somehow here the only thing to remember is that in this stochastic gradient dynamics, there is a strong part that which is the gradient term, which brings you down in energy, and you're putting in a little bit of noise, but somehow not enough in order to have a system that really is at a high temperature. In the end, I mean, what you are sampling is some Gibbs measure with a temperature of order eta. So something which would be, well, I cannot really write it down because here the covariance depends a bit whether it depends on the state or not. So I'm happy not to discuss it too much here. Because in fact here, but this covariance matrix, in fact, depends on theta. So I mean, that complicates a bit the mathematical analysis. But so in the end, if m is not too small, you can really think of mini-batched gradient dynamics as being some stochastic gradient dynamics, but with a noise term which is not too large. And so this explains why you can still concentrate on something that is close to a local minimum. So essentially, if I'm replotting my picture, there would be some local minimum here, and your dynamics in the end would would navigate around the local minimum, not really stop there as in gradient dynamics, but it would wander around with typically something which here is of the order of square root of eta over m. Typically, something like that. So the smaller the learning rate, the larger m is, and the more you concentrate around local minimum. Well, that's the general kind of thing on mini batching there. In practice, that's not what is done exactly. The reason being that, well, maybe you would prefer to ensure, I mean, there are a lot of random things to sample at every step, and maybe you don't see all the data points. So there is a last way. I mean, the practical way of doing this is to do some shuffling. And so typically you have your n data points. So 1, 2, to little n. And you're going to do a random permutation. That's the shuffling aspect. So then you have indices, new indices, still m of little n of them. And then you're going to work with batches of size m. And so you have n over m batches of size m. So it's and then you're still, so this defines random sets I1, I2, etc. until I n over m. And here, of course, I'm pretending that n over m is an integer. And so you will do n over m steps of the gradient of SGD, of the stochastic gradient dynamics. So you will update theta with a gradient that's estimated with the points in I1. Then you will update again with the points in I2, etc., and so on and so forth. And so this corresponds to what's called one epoch. So one epoch in machine learning is one step of the stochastic gradient dynamics where you went over all data points once and only once. So exactly once over each data point. So if you have well, if you have like a million of, well, 10 to the 6, if n is equal to 10 to the 6, and my mini batch is like 100, one epoch corresponds to 10 to the 4 substeps of the gradient dynamics. See, so I mean, there are a lot of things happen in one epoch. Huh? So it's not like you're running, sometimes you see ML results which are reported for optimization over only a few tens of epochs. Well, it can be particularly long to do one epoch, and it's not because it's only a tens of epochs that it's like a few tens of steps. I mean, a lot of things happen in one epoch.
Go over all the data, what you gain by having different batches, because at the end the gradient is linear with respect to.
Yeah, I mean the point is that it's still you still have done approximately 10 to the 4 subsets of the gradient dynamics. So that's why I'm saying that a lot of things happen in one epoch. It's I mean there really have been quite a few updates on the parameters, and it's much better to do that than just do one step of the gradient dynamics with all the points, which would take a particularly long time to converge. And so I mean there are two things. I mean there you can do more steps. I would say that's the prime interest. The other thing is in fact that you're injecting a little bit of noise, and that's a part where I can be less assertive to say things politely.
Some hypotheses on the data
I mean, it's observed that you're going faster. I mean, I have a few convergence results, but the effect of the mini batching on the convergence result is never, but it's maybe not that clear. It's really the fact that you can do more steps. I mean, that's the main perk of stochastic approximation.
For all type of function f, you don't have to have properties on f to be sure that it works.
You mean convexity and so on? I mean, yeah, for theoretical guarantees, typically you will assume some form of convexity. In practice, you never have it, or you almost never have it, and it's still observed to be the good practice. I mean, I don't know anyone who trains neural networks without mini batching, for instance. For some other ML models, people maybe don't use mini batching, but for neural networks for sure. And so the other advantage of noise is that maybe you have some form of regularization. So neural networks, typically, I mean, when you have ML models in very high dimension, typically those for neural networks, you typically have a lot of critical points. I mean, it's rare. As the dimension increases, it's more and more rare that a critical point is a local minimum. I mean, just lots of critical points of a higher order. And the fact that you have some noise is something that helps you somehow go out of local critical points, and that smoothes out the energy landscape. I mean, that's the smoothing property of the noise. So noise is, can be seen as a benefit. Somehow in a landscape like that, a gradient dynamics will always get stuck in local minima. And when you add noise, then you smoothen out things, and maybe you can converge to better minima. I mean, a wider minima, which somehow have a larger free energy if you think in thermodynamic terms. So that's well, I mean, but all those things, I mean, it's a bit speculative. You can see it from the movement of my hands. It's difficult to really give you actual results on that. But I mean, the actual practice is it's clearly doing these shuffling things, mini batching, and then running dynamics with that. Yep. Yeah. No, that's But then I mean, it depends on the height of those barriers and so on. It can be enough to. Yeah. So at each epoch. So one epoch is really that, and so I mean here I would say here you go from theta t to theta t plus 1, and then from theta t plus 1 to a theta t plus 2, etc. So you go that order. So one epoch is really I do this random perturbation. I take the first mini batch, I update the theta, then I take the second mini batch, I update the theta, and so on and so forth. And so when you've done that whole thing, then you start again. One thing here is that I've presented everything for a fixed learning rate. There are various strategies. I mean, here I'd say that there are various optimization algorithms. And I'd say that there are two most common ones. So there is stochastic gradient dynamics with possibly non-fixed, possibly variable learning rate. So some people, I mean here the discussions, it starts to be a bit of tricks of the trade kind of discussion. So if the kind of things that is passed on from one generation of scientists to the other by discussing, and the practice is to use things like that and so on. So as a mathematician, we tend not to have that. It's other fields, they have that. So I mean, here I can only say a bit, give you a flavor of what's being done. And the book by Benju, Courville Goodfellow, would be a good place to read about, to give you one feeling of how it's done. So learning rate, I mean, some people would say that maybe initially you need to start with some small learning rate because gradients are large, because you're far off a local minimum. And then as you come closer, gradient decreases. So maybe you can be a bit more aggressive on the learning rate so that optimization is not stalled. And at the end, when you start really converging, maybe you should reduce the time step so that you really converge to something and not just start oscillating around the local minimum. So what I just said seems like a good practical sense. When you want to make that into a practical recommendation, it's a bit more difficult. And so people have schedules for eta where sometimes it increases, decreases to shake off the system and so on. But those are like schedules which are decided beforehand. So I mean, in any case, SGD is one option, and then you have Adam, which I'm going to describe more or less next. which is the other method that, which is like the default method for neural networks. So one, well, I don't know how much you know about optimization, but one gradient dynamics sometimes are a bit slow because they miss inertia. So it has been observed, and somehow there is some practice about the interest of inertial dynamics for optimization, and this goes back to Nesterov in the 80s. Hop, Nesterov in the 80s. So somehow, because you're people from chemistry and physics, this part is much easier to teach because essentially what those, when you see them with the eyes of love and after some translation, those kind of inertial dynamics really are dissipative Hamiltonian dynamics. So that's, we know, which is common sense to us here. But well, some people in machine learning, I mean, they still need some motivation for that. And I mean, intuitively, I mean, those inertial dynamics is like when you go down skiing down a mountain, typically you're not really following directly the gradient, but naturally you have some inertia and you navigate a trajectory that uses, well, that does not really rely on the local gradient, unless the snow is really, you know, like a powder snow that just flew down. There is a lot of viscosity, and then maybe you're forced to follow more directly the gradient. But the more icy it is, the more inertia you can use, and then you navigate extremely differently on the snow, whether there is ice or not. I'm not a good skier by myself. If you've never been skiing, maybe this intuitive explanation is not one. So maybe I should think of something else like, but yeah, I don't have any other good option there, something that uses going down and navigating around. So Hamiltonian dynamics, I would say so Nesterov. So dissipative Hamiltonian dynamics would be something like that. So the derivative of theta, I tend to call it omega, like, you know, in good old physics, like makes more sense. And then omega t would be minus gradient f of theta t. So that's the Hamiltonian part. And then typically you would add some friction here. So psi strictly positive, which is some friction. So you have one part here that preserves, so this part preserves the Hamiltonian, which would be f of theta plus omega squared over 2. And this part decreases the kinetic energy. And so the hope is that in the end, you converge to a minimum of f because you've taken out, I mean, any kind of potential energy that is left in f, you kill it by decreasing the kinetic energy until there is no energy left. So that's the dissipative Hamiltonian dynamics. And now I'm going to write the Nesterov scheme. And after, because I mean, Adam and so on, it builds upon that. And so what we will see is that the Nesterov dynamics is something that is a discretization of that Hamiltonian dynamics. So the way it appears in the literature is that omega t plus 1 is beta omega t minus gamma gradient f theta t plus beta wt, and then theta t plus 1. So it's a partition, what's called a partition scheme. So we update one variable and then the other. Then theta t plus 1 is theta t plus omega t plus 1. And here in this writing, you have that beta is a number between 0 and 1 excluded. So that's the Nesterov scheme. And, you know, I mean, Russian scientists, the 80s, I'm not so sure how we came to that.
Theta t plus 1 and t plus 1 again?
No, I don't. was just to check that everyone was paying attention. You do, congrats. So now let's try to, I mean, and that's how you will find Nesterov's dynamics in the ML books. So I mean, to me, having that in mind, I eagerly want to make a connection. So the way I'm making the connection is that saying that, okay, let's consider beta is equal to exponential minus psi square root of gamma. I'm not saying that that it's completely, I mean, it took me a bit of time just to work out how to go from one to the other. You can see that here there is no time step, here there is a time step gamma, and so somehow here there should be a time step, and so this one is maybe the square of an actual time step. To what?
The same discretized or
No, I want to see this as a discretization of that, and it's not immediately clear because here you see, for instance, there is no gamma in front. So I mean, the way I'm doing it is that I'm writing. So here maybe the notation is not great. Maybe for Nesterov dynamics, maybe I'm putting bars on the omegas, and then I'm saying that this omega bar, in fact, it's a square root of gamma of an actual omega. I'm just rescaling what naturally appears in Nesterov dynamics. And so when I do those, and this number beta between 0 and 1, I can always re-express it that way. So this defines the psi. I have a gamma, and so this defines the psi. And so when I do that, then I have that omega t plus 1 is equal to omega t plus beta minus 1 over square root of gamma multiplied by square root of gamma times omega t minus square root of gamma gradient f theta t plus beta square root of gamma omega t. Let's make sure that this is correct. Yeah, I forgot one, you mean? Here, this one? On the left, yes, on the left, I mean, this is Nesterov scheme, so it's working with a theta and an omega bar. So I'm updating omega bar and then theta. And then if I haven't messed up things, I can rewrite it that way. The point here is that, I mean, this term will go to 0 when gamma goes to 0. Here, square root of gamma, it's fine. This term here, because beta is exponential minus psi square root of gamma, when I do minus 1, I divide by gamma. This will be converging to minus psi as gamma goes to 0. And I want to think about the gamma goes to 0 limit because that's the continuous time limit. Voilà. So I mean, then this thing is more or less omega t minus psi square root of gamma omega t minus square root of gamma gradient f theta t. So you can think of it as a discretization of that using a time step square root of gamma. So that's rather reassuring. No, you know, whether the discretization is exactly this one and so on. So I'm leaving that to Nesterov. And the other thing is that theta t plus 1, it's theta t plus square root of gamma omega t plus 1. So this as well is a discretization of that first line with a time step square root of gamma. And so this scheme, this Nesterov dynamics, is a discretization of dissipative Hamiltonian dynamics. Let's call that DHD with time step square root of gamma. So that's what it ultimately is.
A quick question. So we were wondering if you can compute the gradient of low cost because it's a mini batch. Can you also do like approximate certain methods?
Yeah, I mean, Adam is precisely something like that. It's like a dissipative Hamiltonian dynamics with a mini batch estimator for the gradient and some renormalization procedure to precondition. I'll inflict you the Adam dynamics as well. But I mean, for the moment, I kept it simple without mini batching. I mean, Nesterov, no one uses it as such in practice in ML, but it's I mean, it's a good guideline about you know, like when people want to introduce inertial dynamics, heavy ball or whatever they call it, they usually start by Nesterov. But somehow it comes out a bit out of the blue. If you, I mean, ML books on inertial dynamics, I don't find the presentation particularly convincing. Let's put it that way. Alors, so I mean, somehow to go beyond SGD, the first ingredient is inertia. So we already have an ingredient which is mini batching. We have inertia, and then there is a last argument, last ingredient, which is some form of preconditioning. So it's often the case that we have a highly anisotropic landscape F. I mean, this should not come to a surprise, especially when in high dimensions. There are typically directions in which the gradient dynamics can move more freely than others. I mean, sometimes gradients are really large, and so you have a dynamics which can only navigate in narrow channels, and other regions of the space, the gradient is not as large. So there is a strong anisotropy. And so if you have an anisotropic dynamics, typically you would prefer to consider, for instance, if you work with stochastic gradient dynamics, you could think of considering something like that. So instead of just pure gradient dynamics, I'm multiplying by a matrix M-1, which is a SDP, a symmetric definite positive. So typically here, this dynamics has the same stationary points as when there is no matrix M. I mean, you stop when gradient F is 0. And that's the only moment where when you can stop. But maybe it's good to have this M-1, which typically, I mean, you could think of it as the Hessian at theta star, if this Hessian at theta star, so some local minimum is indeed a symmetric definite positive. So if you have something like that, somehow you, I mean, let's consider an example. An example is probably a better, is more convincing than something else. Let's think about a quadratic potential, something like that, theta minus theta star, with A, which is which has a very bad conditioning. Conditioning being the ratio of the largest eigenvalue to the minimal eigenvalue. So typically, when you have a quadratic potential in high dimension, you have a wide range of eigenvalues for A. Just life like that. So if you look at gradient dynamics, you have something like theta dot is equal to minus A theta minus theta star. But let's say here I can fix theta star to be 0 just by shifting my variable theta. So I can, without loss of generality, think of theta star as being 0 if I work with the shifted variable theta minus theta star. So I'm just making that so that the gradient dynamics is really this simple theta dot is equal to minus A theta dynamics. And then if I, if I diagonalize, I see that here the convergence is hindered by the smallest eigenvalue of A. So that's the thing that is going to make the convergence smaller. But now if I discretize in time, theta t plus 1 is equal to theta t minus eta A theta t, I will have limitations on the time step here because I will need a condition like 1 minus eta lambda max of A. This should be smaller than 1. Because if it's not smaller than 1, then I will have some exponential increase in one of the directions. And that's bad news for the convergence. So typically, when you have a dynamics like that, bad conditioning, I mean, and somehow it's sufficient to have the condition on lambda max and lambda min, both in absolute value smaller than 1, to make sure that here you have convergence. But when you need to satisfy both things, this limits a lot the time step, which should then be of order, essentially, here this condition means that the time step should be of order 1 over the maximal eigenvalue. And one way to alleviate that issue would be to work with m equal a. Because if you work with m equal a, then you have a dynamics which is just theta dot is equal to minus theta. And that's great news because then you have it's an isotropic thing. Convergence is of order 1. You can really use a time step of order 1. You're not limited to really small time steps because of the largest eigenvalue. So that's, I mean, preconditioning is really something that's useful in numerical methods, particularly in linear algebra to solve linear systems and so on. And it's something that is there to make sure that you better behaved. And that's particularly important for optimization in high dimensions. And so Adam, I mean, it's really this. It's stochastic gradients. It's momentum or inertia, so introducing some extra variable. And it's a form of diagonal preconditioning. Conditioning. And so those are really the 3 steps that make Adam work. Adam, I should say, so it's 2014. So it's something that's pretty recent. And it's still a preprint. In fact, it was presented as a poster at a conference. And after that, they did a preprint, but they never really cared to publish the paper. And now it's like 80% of neural networks are trained with that. But somehow this shows also that people who came up with Adam, I mean, I'm not so sure how they came up with that method, but it's not like they were clear and confident about wow, this is going to be a game changer for optimization, which it turned out to be, but it was I'm not so sure it was anticipated like that, given the publication history of the paper. Alors, what does Adam look like now that I've piqued your interest about it? So the update is the following. So it works component-wise. Component-wise, I mean, that's a trace of the fact that there is a diagonal preconditioning. So that's why I'm explaining component by component how it works. So minus gamma, well, maybe I should have written eta, but I mean, anyway, this gamma here, it's the learning rate. Sometimes it's eta, sometimes it's a gamma. I agree, and not always consistent. So there's something called Vt minus 1k, and then there is an epsilon plus square root of St minus 1k. So here, epsilon is a parameter. It's typically 10 to the minus 6. Voilà, just to make sure that, to avoid dividing by 0. When you have a number that small, I mean, it's just a sign that, you don't really care about it. And that's the default choice in any Adam implementation I've seen. And then 2 things. So here, this VTK, it's running somehow a running average of the gradient, of the stochastic gradient. And the S, it's also a running average, but of the square of stochastic gradient. So I mean, and that's where the preconditioning enters. The fact that you have the gradient that you're essentially dividing by the square root of the norm of the gradient squared. So that's something to somehow select a direction. So you can think of this as being like a vector with a unit components. I mean, this thing should be thought as being order 1, more or less always, whether you're in regions of high or low gradients. It's a way to renormalize the gradient. The other thing, here I've said running average, and this really is, or maybe I'm doing another, hop là, voilà. That's the inertia part, because the running average means that you're keeping a big track of what has happened, at least in a recent history. So what are the actual formulas for that? That is VT, it's a beta 1 VT minus 1 plus 1 minus beta 1 G hat T theta T minus 1. Voilà. And that's where you see, and so beta 1 here is a number between 0 and 1. Typically, so the default choice would be 0.9 for gamma equal 0.3. So the default choice for Adam for the learning rate would be 10 to the minus 3. Here you can really have a default choice because you, thanks to this preconditioning procedure, your gradient has entries of order 1. So you can think of all properties to be of order 1, and that's why you can suggest, you can be so bold as to suggest a default time step. And in practice, I mean, by playing around with it, I mean, between 10 to the minus 2 and 10 to the minus 4, indeed, I mean, those are kind of typical choices for a time step. So beta 1 is some parameter. In fact, in the original Adam method, people don't really write it that way, but I tend to think of beta 1 as being some exponential minus alpha gamma, so alpha 1 gamma. So that this, what is here is more or less something like dVt is equal to minus Vt dt plus power. So something like that. Between quotes to some extent, because GT, it's a random quantity, but I'm thinking of something like that. So then Vt is some exponential integral of GT. So if you write it, is it clear for everyone the link between those two? Otherwise, maybe I'll rewrite it like Vt minus 1 divided by gamma. That thing is beta 1 minus 1 divided by gamma, Vt minus 1, plus 1 minus beta 1 divided by gamma, Gt hat. And if my B1 is of the form exponential minus alpha gamma, I'm plugging this inside, passing to the limit as gamma goes to 0. For this is converging then to minus alpha. And this here is converging to alpha. I realize I forgot a factor alpha. Okay, and so when you have a dynamics like that, you can analytically integrate as Vt the integral of exponential minus alpha t minus s, so from 0 to t of gs alpha, something like that. And that's where you see that you have a running average of G. With some emphasis on the recent history, because that's where the exponential here is the strongest. Ouais. So I mean, that's why I'm saying that this formula here for the update of V really corresponds to some form of exponential average of the instantaneous estimate of the gradient. So the nice thing with when you average stochastic gradients is that you filter out a bit the noise. So that's one advantage. The other thing is that you keep some memory, as in my skiing example, and which is observed to be a good thing when you do optimization with inertial methods. So that's the first formula for V. And then you have another formula, which I'm maybe writing here, which is really extremely similar for S, except that it's with square gradients. So you have STK is equal to beta 2 st minus 1k plus 1 minus beta 2. So until now, it's really it starts the same way, but now I have gtk theta t minus 1 squared. So it's really the average of the squares of the gradients, components by components. So this gives typically for the average, the scale for the average of g squared. And that's why when you divide v by the square root of s, you can end up with something of order 1. And here by the default value for beta 2 is something that's a bit closer to 1, so 0.999 for gamma equal 10 to the minus 3. And I'm really thinking of beta 1, beta 1 and beta 2 as being some exponential minus alpha 2 gamma. And so this means that alpha 2 is essentially of order 1 here. And alpha 1 is maybe is a bit larger. It's maybe of the order of 10 or 100. I know some people have been using that for other kind of optimization problems. I'm not sure how successful it is outside of the ML realm. In particular, here there is this kind of averaging things and so on. It's a bit tailored to, but it particularly has in mind that you are using stochastic gradients. So if in some other optimization problems, you're not really using stochastic gradients, maybe Adam is not the right thing to do. But maybe it is. I mean, there is still the preconditioning idea and the inertia. But say that if you have never used it before, just give it a go and maybe, life is full of surprises. But I mean, I've been trying it on toy 2D examples and so on, and was never so great. So I mean, maybe there's something also related to the dimensionality of the problem and the structure of the landscape, that you have lots of critical points and so on. So there is some mathematical analysis for the performance of Adam, but it's still well, it's not so clear, I would say, because usually the mathematical analysis can only be made in situations where f is convex, and then there are lots of things that you lose with respect to practical problems. So it's only observed that in practice, for MLs at least, for neural networks, that it's extremely efficient and difficult to beat. But as to why this is the case, it's a bit more mysterious. Yep.
This way, the K was introduced an index.
It's one component. Yeah, so it's component-wise. So here I'm working. I should have made that precise. I'm working components by components from 1 to D. And that's I mean, the one place where you see that it's component-wise is just for the S, in fact, because then I'm just querying this entry of the gradient. All the other things could have been done in a vector way. And somehow it's just for notational convenience, because I could have introduced some kind of a diagonal matrix S and written everything like that. But any question on Adam at this stage? So I'd say that this there is an extra twist to it, which I'm probably going to spare you, is that in practice you're often starting from let's say twist, there is some normalization here, because in practice, what would you start with is essentially V0 equal S0 equals 0. Your first iteration, you don't have any idea of the average gradient or the average square gradient. And so somehow your exponential average is starting from too low a value. You start from 0, then you ramp off a bit. And there are ways of unbiasing a bit things by considering variables like updating not with a VT, but a VT hat, which is VT divided by 1 minus beta 1 to the power t, and a similar things for S2. And the fact that you divide by this factor is really just to compensate for the fact that you start from 0, this kind of moving average. So if you want the full argument. I mean, it's in the lecture notes. I mean, I'm inflicting you the computation there. But I mean, just to have in mind that people do that in practice to compensate for the transient effect of the moving average at the beginning. But I see it merely as, some kind of a local patch rather than a genuine feature of Adam, because for me, the genuine features of Adam are really those three, and the rest is a bit how you scale things up. But sometimes in the ML presentation, it's a bit difficult to distinguish those two aspects, and I've sweated a bit on that, so that's why I'm hoping that this remark helps. Voilà. The other remark I have is that in practice, when people do hyperparameter tuning on Adam, you will see, I mean, there are in fact three hyperparameters, to be clear. There is the learning rate, gamma, beta 1, and beta 2. And to me, the way I'm doing the hyperparameter tuning is more by working with alpha 1, alpha 2, and gamma. So I really see my beta 1 as some exponential minus alpha 1 gamma, motivated by the time continuous limit of Adam. And so I'm playing on the alpha 1, alpha 2, and gamma. I've seen people, I won't give names, doing hyperparameters, I mean, fixing beta 1, beta 2, and only playing with gamma, but that's somehow a bit inconsistent if you think about the continuous time limit. And so in particular, there is one paper by Da Silva Gazo in 2019, if I remember well, where they really make the argument that you should be, that those are the three parameters you should be doing hyperparameter tuning on. But yeah, people don't do that. Yeah.
Do you tune all three, or you keep alpha 1 and alpha 2 fixed and only tweak gamma?
So if I was to tune only one, I would suggest fixing alpha 1 and alpha 2 to the default values. So here, if this is a gamma bar, this is a gamma bar. And so you look for the alpha 1 such that exponential minus alpha 1 gamma bar is equal to 0.9. So this defines alpha 1, same for alpha 2, and I would fix those two values and then play with gamma.
You fix beta 1 and then play
Yeah.
with gamma and get the alpha.
No, I would refix alpha 1, alpha 2, meaning that in practice, I would, when I have a gamma, then I would consider a beta 1, which would be beta 1 to the power gamma over gamma bar. You see? So that's in order not to change the alpha 1 and same for alpha 2. But again, I mean, it's not like I have seen many people doing that, but yeah. My understanding of the continuous time limit of these dynamics really forces me to think of it that way. And I was glad that some authors at least recommended doing that. But I think that's more or less all what I wanted to say about optimization methods. Of course, there would be more theorems to give about convergence and so on, but I chose not really to talk too much about them in those lectures. But if you know, there is a good, an excellent chapter in the book by Francis Bach about the convergence of various methods here. Fortunately, I'd say in practice, you never think about implementing those methods because in PyTorch, I mean, you just call Adam and then it does it for you. And in scikit-learn, I mean, you even have other kind of optimization method. I mean, for each of the ML method that exists, there is a dedicated training method in scikit-learn. I still find it relevant to know what's behind under the hood in terms of optimization when you have a large neural network, so that you have some idea of where it can fail. And it can definitely fail at various places. Early stopping maybe to conclude the part on optimization. And it's maybe a point I should have made earlier on, is that let's look at typically the loss as a function of the epoch. So you will have something that is random, because of the mini batching and so on. You have a gradient noise. And so optimization will typically be a bit random, but you should see a trend. Hopefully, you should see a trend on the validation error. So that here, sorry, on the training error. So that's a training error. And somehow, as usual, there is another thing that you monitor, which is the validation error. Meaning that this is the error. So, for instance, the mean square error on the validation set. And so at every epoch, you're computing that error as well for this validation data that you have on the side. And you would typically observe behaviors like that. So the training loss decreases, maybe at some point it's stalled, and the validation error, same thing, it decreases, and then maybe it's stalled or maybe it even slightly goes up. And so there is the notion of patience. So at every epoch, you compute the new validation error. If it's smaller than what it was until then, that's your new best validation error. And then you proceed. And after a certain number of iterations, something which is called the patience, if you have not decreased the validation error, then you stop the optimization procedure. And you go back to the point where you had the best validation error. So your champion is this one, is the state at this epoch. So the way optimization is done then in ML, in particular for neural networks, is that you really keep track of those two quantities. And if you have not decreased the validation error for a certain number of steps, epochs called patience, you go back to what was the best thing. So you're not taking the configuration of the neural network at the end of your optimization procedure. You're really going back to, like the best candidate along the way. And with all this, there is some form of here a maximal number of iterations. So if at some point you haven't decreased for a certain number if you're still decreasing the validation error somehow, then usually you're being capped by the maximal number of iterations. Just a safety procedure, but if that's the termination criterion, it's a sign that you should go on, that you haven't been converging. And so the way I would say it's done in practice is that you do to choose the parameters. I mean, there are lots of parameters for the optimization procedure, as we've seen. Parameters like mini batching rate, rate M. Then you have the learning rate gamma, and then maybe you have extra parameters like alpha 1, alpha 2, or beta 1, beta 2 for Adam. You see here, and the patience. At this stage, we have at least 5 hyperparameters to tune to get the best result. And so the way it's done is typically by cross-validation, by running those kind of simulations, checking the best validation error for the various choices, and then keeping the one that leads to the smallest validation error over the hyperparameters you've been looking for. Mini batching rate, typically you don't play with it too much. I mean, it's like 2-3 values. Same for patience. And maybe you're also keeping those extra parameters as being fixed to the default values, alpha 1, alpha 2. And so then it's really more on the learning rate that you're playing a bit. And also maybe you don't do a full optimization to set up the parameters, but maybe you do an optimization only for a few epochs, and you look for what's most successful after a few epochs to set, I would say, the less important parameters, like mini batching and those extra parameters. And maybe for the patients, you only try 2 values, and you do that only once you've identified more or less the correct learning rate. I mean, I'm saying that because when you have like 5 parameters to look upon, you definitely, and all this is only, as a bit of a fine-tuning of the optimization procedure, because after that you have all the other hyperparameters of the model, like topology of the neural network, activation functions, I mean, dropout rate, regularization rate, you name it. In the end, the list of hyperparameters to tune is extremely long, so you have to come up with, how I say, principles for how to set them, and that I mean, you can easily be caught in months of efforts of trying to set all the hyperparameters if you don't take things in a principled way. I mean, that's typically for neural network. What I would suggest is that you go with two extreme architectures in what you will be considering, and you make sure that your choices of parameters are more or less correct for those extreme architecture, and hopefully they are for anything that's in between. So if by meta you mean something like that, yes, that's my approach to it. But you know, I mean, there it's yeah, there is no easy answer to that question.
Imagine you have like a great data set where the learning error and the validation error, they go to zero infinity. You don't put like a maximal epoch or a tolerance that you want to reach.
I mean, they will never really go to zero because of the stochastic gradient error.
Yeah, okay, but
think-
when we do this in deterministic problem, you always have like some like Garde-fou.
Here you have a redetermination criterion and which are in relative value and for which you have somehow ideas that it should be. No, not really. I mean, here it's really a validation. And here, I mean, we're doing a regression. So the validation error is more or less clear. But you could also imagine, you know, training a mean square error and validating on a mean absolute error. And for classification, people go for some loss, which is a convex surrogate of the actual loss, and then they report some accuracy. So fraction of 0.1, that's correct. And so the validation can be of really a different nature than the quantity you're actually targeting. So I mean that is some benefit because then you don't have to optimize this non-smooth function like a mean absolute error, but it also comes with some issues, I'd say, because it's in the end you don't really have a scale for what the correct value of a validation error should be. You just go for the best, for the best you can achieve. ML is a bit of a pragmatic field, huh? But I mean, there are some good things with being pragmatic.
And right, but you're looking for local minimum is this Rn minus omega, with omega, right? So wouldn't you have
So minus omega is
the loss function, right? It's big F that you're
yes, but I mean here for early stopping, it's really I'm not looking at the regularization term. I'm only reporting the actual loss. I mean for the validation error here, it's only it's unregularized.
like local minimum like this, but then it would go down again.
Yeah, maybe. I mean, typically for neural networks, when you look at, I mean, if you've been playing with a TensorFlow, there are many situations where you would see the optimization stalled, and then you really go down a plateau and so on. So that there are really abrupt changes in the. I mean, life is never that easy in practice. I agree. I'm trying to make, you know, a good teacher is a good cheater. Once someone once told me, and I'm trying to apply that rule. I see that some people don't like to cheat in the room, and that's great. But any other question on optimization before we go to the heart of the matter, which is unsupervised? So last part of it. So I mean, this concludes somehow everything I wanted to say about supervised learning and regression. There is something I did not discuss, which is supervised learning and classification, although you have now, you know, lots of things I have been saying applies there. Now we go out of the supervised world and go to unsupervised learning. So I thought of doing some clustering. We'll see whether I have time for that. I doubt I will. So I'll directly go to really the main topic of interest, and when this is done, we'll see what's left. So we'll really focus on dimensionality reduction, which has, I mean, to me, there are two main applications for that. There is one which is related to the scalability of the algorithms or the computational reasons, and the other one, which is related to interpretability. Meaning that in some situations, you want to reduce dimensions because some methods cannot be used in high dimension or their computational cost explodes and you want to reduce dimension. And so if you take the example of the MNIST data set, you know, those images of digits, it's a problem in dimension 784 we've seen. But in fact, there are lots of white pixels. I mean, it's digits in black and lots of white pixels around. And some pixels are also consistently black from one image to the other, whether it's a 7 or a 8 or a 6 and so on. So you don't really have an actual dimension of 784. And so it makes sense to decrease a bit the dimensionality to run cheaper methods and also maybe to be able to run some methods which would not be you would not be able to run on the full problem. My motivation though today will be more on the interpretability side, meaning that I have in mind that I will have a molecular an atomic system with lots of degrees of freedom, say a big protein in a solvent, so millions of degrees of millions of atoms, millions of degrees of freedom. And I would want to understand really what makes one conformation of the protein different than the other. So typically I'm working with people from Sanofi, so pharmaceutical industry, and so some proteins, I mean, really change function just by moves a few changes in the conformation. So one loop changing, and this can completely modify the chemical properties of the protein. So I would really, that's the kind of thing I want to understand. And, you know, like the key, identify the few key relevant variables in an otherwise complex system. So we first go for a linear method, which is principal component analysis. Component analysis, which is, I mean, it's for the mathematical culture, something that's always, it's useful to everyone. And sometimes it can be even directly relevant in practice. What I would say about PCA is that, you know, before you go to something fancier, like autoencoders, as we'll discuss, you should always try PCA because maybe it could work. And if it does, then, you know, it's a principle of scientific life that you go with the simplest method if it does the job, and otherwise you go to more complicated methods, but at least you have a motivation for why you need to make it more complicated. Who's familiar with PCA among you? Well, okay. So what I'm hoping for, no, and let's not be that way. I will present PCA in a way that maybe was not the way you've seen it. Because I used to teach it differently as well. And so now I'm going for that. That's because it's the natural way of extending to the nonlinear setting. So I will think of input points x like that, so which will be row vectors of dimension d. And so what I want with PCA, what PCA does, I mean, you would say, okay, I'm trying to identify the highest variance direction in the covariance matrix of my data, something like that. What I want PCA to be, in fact, is something where I start from a high dimensional data x. I run it to something which is much smaller dimensional, so using some encoding, and then I'm decoding it to something which is of the same dimension as the original using some decoder. And because I mean, with that diagram, you can see easily where I'm getting to in terms of neural networks. But we'll do that with matrices first. And my claim is that what you know about PCA, constructing covariance matrix, diagonalizing, and so on, it's just doing that with linear neural network somehow. Alors, so it's about reconstruction. So for that, I'm thinking of a variable like that. I will consider some variable z in R1 to L, So L will be the dimension of the latent space. The latent space, it's how many directions you retain in a PCA. And so it's something which is strictly smaller than D, and usually you would want it to be much smaller than D. And so I will think of Z equal X E, with E a matrix which will be of dimension D times L. So that's this encoding part. It will take a data point in high dimension and reduce it to some latent variable Z in much smaller dimension. And spoiler alert, it is going to come, this will be the principal components, if that rings a bell for those of you who've seen a PCA. And after that, I want to decode. And so I will think of a reconstruction which will be ZD with D be in RL times D. So the ZD will indeed be an element of in the original space. And to that, I need to, if my data is not centered, I need to add some bias or shift. Because I mean, here what I've been presenting is that I have a data centered on 0. I end up with something that's still centered on 0. But usually your data sets are not centered on 0. So you need to take that shift into account. But overall, I mean, that's really the idea of, and in neural networks, I mean, you naturally have the shift in mind. So the loss I'm going to consider here is something where I have 3 parameters to fix: an encoder, a decoder, and a shift. And I will want to my mapping to reproduce the identity. So I want that when I take my point, I encode it, I decode it, and I shift it, that this quantity here is minimized. So this can be considered as some reconstruction error. And that's why, I mean, this will be, we will see the same similar formula for autoencodes. Well, in fact, let's kill the suspense immediately. B will simply be xn bar, so 1 over n, the sum of the xi's. That part is, I would say, easy enough to see by computing here the gradient with respect to the B variable and doing the algebra. So this comes from gradient with respect to B of Rn hat equals 0. So somehow an intuitive way of saying it is that the function which I actually care about optimizing is a function just of E and D, and it corresponds to considering data points which have been recentered. And those recentered data points, you do some linear transform. So they're still centered. And that makes sense. I mean, if you have points around 0, you're going to reconstruct them with something that is also centered around 0. Maybe good time for a break before I embark myself in a long derivation. Please come back with full of energy.
Moi, je suis un peu déconcentré sur le